Okay, let's get the show on the road. Hello, everyone. Hope you're well. Welcome to another edition of Math 1203. Last time, just as a reminder, I already graded your test and I sent those guys out some point over the weekend. I would encourage you to look over them, make sure that everything is fine, that I graded everything. You should be able to see the grading rubric and everything that I used. So you should be able to look through your exam, see everything that you would have gotten points for or would have gotten points taken away for, and just kind of, make sure that everything was graded correctly. And then you can use the read grade request feature to submit any issues with those exams. So that's how I would recommend to do it. And I sent a link to an instruction video on how to actually do that, but it's actually really simple. You just look to the bottom right corner of the screen, and there's going to be a button that says read grade request on each particular problem that you're looking at, and you just click on that, and then you type a message to me to let me know why you deserve more points or whatever. So yeah, you can do that, and we will be good. That being said, let's actually just jump into the lesson. Okay, there we go. Everything's good. I think this was where we were last time. I left you with an example to do. Which now I saw, was it maybe 2 people? So I saw a couple people. I don't remember exactly if it was 1 or 2, because I grade question by question, and to in the interest of fairness, so I grade 1 question at a time. I grade everyone. I don't really look at the names. Some of you actually wrote your names on the scans, so that made it hard. Or it didn't make it hard. It just it's like, okay. I wanted to not look at the names while grading, to avoid favoritism and all sorts of things. Well, I don't tend to have, but you always have to account for your biases. So yeah, I graded question by question. So I saw this technique come up a couple times. I'm not exactly sure if it was with the same person. But yeah, the technique I'm about to show you, I actually saw 1 or 2 people actually use it in the exam. So I don't know, maybe you guys can tell me how you would go about finding this derivative. Or maybe there's just a nice little rule we could use to take the derivative here. So what do you guys think? Ideas? So I'll tell you one thing not to do. Mistake. Or I should state it as common mistake, because it is in fact a common mistake. As soon as we'll see something like a ddx of x to the x, and there will be like, oh, power rule. I can take this x, move it down, subtract 1 from the power. Yeah, this is incorrect.
So control log.
Hold on. This is incorrect because it's a misuse of the power rule. says d dx of x to the n is nx to the, am I going to be able to fit all that? d dx of x to the n is equal to nx to the n minus 1. Now, here though, your n is a constant, and your x is the independent variable. In x to the x, the power is not constant. So this rule does not apply. Okay, so that is the first thing. So very common first attempt for students to do something like that, just try to use the power rule. Another semi-common, it's not as common as the first one. The power rule, students do the power rule all the time for stuff like this. It's like, I can't count how many times I've seen that. But another common mistake is to have this, and then here they try to use erroneously. That d dx of a to the x, well, that's a to the x ln a. And so they would say, oh, x to the x, that must be x to the x ln x, right? So I can use a natural log here by doing this. The problem is, though, here, your a is a positive constant. And x is your independent variable. Right? And in x to the x, the base is not constant. So this rule does not apply. So I wanted to point that out because I saw there are some common mistakes that I see very often with guys like these, and they're rooted in not knowing the rules very well. You have to know the rules very well, as I've been mentioning. Your rules are like templates. They have to be able to fit over the problem that you're looking at, and you have to know the rules so well where it's like, you don't just kind of know the rule, oh, I kind of know the power rule and I can regurgitate it, but you should know what the individual pieces in the rules are. Like what part of this rule is a constant, what part of this rule is a variable, what part of this rule can be any generic number in this situation, or does it have to be a specific number, right? So there are things like that that you have to be aware of. So here, n is used as some generic constant. Here, a is also a constant, but it's a positive constant. It's going to go inside the logarithm. And so knowing these things are also important. You need to know when the rule you're looking at applies. Okay, so now back to this guy. So we've taken away the two common approaches.
So can you use the chain rule?
How?
Well, you have like a function to a function.
A function plugged into a function. Okay. All right. So how would we do that? How would we get that to work here? So the chain rule is kind of tricky. We do use it, but you can't use it directly, because what does the chain rule say? Well, you'd have to differentiate the outer function and then multiply by the derivative of the inner function or something like that, right? But differentiating the outer function is a thing we don't know how to do in the first place. So yeah, we don't have a rule to differentiate the outer function. We don't have a rule to differentiate what something would look like if the base and the power is a variable. We can deal with if the power is a variable but not the base, and if the base is a variable but not the power. But we don't really have anything to deal with both. I mean, you made a suggestion earlier that was on the right track. So I don't know if you want to backtrack and kind of develop that thought a little bit.
With the natural log?
You use a natural log. How would we use a natural log?
You take the natural log of x to the x.
Yeah, well, can you do that? Is that legal though? Like if I give you a mathematical quantity, can you just decide, oh, I'm gonna take the natural log? You have to set it up a little bit more carefully. We in fact did something like this before when I was deriving the power rule for you guys. We did use the natural log to derive the power rule, remember? Because we said the n was annoying because if the n was as small as 3, it took like forever to multiply out. And I was like, what if the n is 100? That's really annoying. And so it's like, oh, if the power is annoying, can you use the log, right? And that, again, is a very common theme. That's something I want to hammer home in this class especially. Logs and exponentials are inverses. If a power is giving you trouble, you use a log. If a exponential is giving you trouble, if an exponential, or which is a power, is giving you trouble, use a log. If a log is giving you trouble, use an exponential, right? You can use these to cancel each other out. But how you use them is important. Like you can't just randomly log something. Like if I lend you $100 and then you give me back like $2 and you're like, oh, I just took log to the base 10 of the $100 you borrowed from me and I decide to pay you back in log dollars. Like you can't do that, right? You're changing the value. Like, no, you're not. I want my $100 back, right? So you can't just log something like that. So what we would do is you would set y equals x to the x, because you're not allowed to log some random expression, but you are allowed to log both sides of an equation, right? So whenever you want to do something that will change the value of something you're looking at, if you're trying to pull that off, what you want to do is you have to set up an equation so that you can balance both sides. Because once you do something, you make a change, you want to be able to undo that. And equations have rules that allow you to undo stuff. Yeah. So you'd start by that. Then yes, we would take the natural log. And of course here we want to find y prime. Taking the natural log is useful because the right side is going to become, well, you can take this power down and bring it, put it in front. Now what we can do, so here, log both sides. Here, simplify left side. Here, let's take derivatives. And now's where the chain rule will come in. It will come in the form of implicit differentiation, because now we know that ln of y is y prime over y, because you have to differentiate the outer function, multiply by derivative of the inside. On the right side, I just had to differentiate this according to the derivative rules. I know I don't have to put any x prime or anything because x is the independent variable. So what I'm going to do is I would do the product rule because it's a product of functions. So I differentiate one function, leave the other, plus leave the first function, differentiate the second function. So this gives me that my y prime over y is equal to ln x plus 1. where the 1 is separate, right? So this is kind of like that. And so, because I want my y prime, I'm going to solve for the y prime. And so what that means is that my y prime is equal to, well, what is your y? Your y was x to the x. So if I want my answers in x, I can plug that back in. And voila, that is my answer, i.e. the derivative of x to the x is x to the x, ln x plus 1. You don't have to memorize that. I'm putting it in a box, but you don't have to memorize it necessarily. Unless you want to, I guess. Yeah, so that's how we would do that. Now, this is a process that we have seen before. In fact, this is how I derived the power rule for you. And we could use, we could use the above method to derive this rule, just as we used it to derive the power rule, right? So the derivative of a to the x, that was one of those things where I just told you, oh, just believe me for now. I didn't actually prove that that was the rule. And I just gave you what the answer is. The derivative of a to the x is a to the x ln a. But you could have derived it. So if we wanted the derivative of a to the x, and you're like, yeah, I know the power rule, but that's when the power is a constant and the base is a variable. What we could have done is set y equals a to the x. This means that ln y is ln of a to the x. This means that x ln a is what the right side is. Then I can differentiate both sides. That would just be ln a, because the derivative of a constant times x is just constant. And then my y prime would just be y ln a, but my y was a to the x. So this gives me a to the x ln a. And so I could have derived that the derivative of a to the x is a to the x ln a, right? And I could use logs to figure that out. But this process is actually a very standard process in the sense that it's not just some random little trick that I can do. It actually has a name. This is what's called log differentiation. That's the log differentiation. Of course, it's short for logarithmic. Okay, which is the title of today's episode, brought to you by Logarithmic Differentiation. It's our today's sponsor. Very nice technique, very powerful technique, and it goes beyond just doing things where the power is an issue, and I'll talk about that in a little bit. But let's actually talk about it. Suppose you have y equals f of x, and you wish to find y prime. You may, right? You don't have to, no one's forcing you to do this, but you might find this convenient, is to after you set y equals f of x 2, log both sides. As in ln, quote. 3, simplify the right side. Did I type right side last time? I think I typed left. Simplify the right side. Right, the right side is going to be the issue, right? The guy we want to rewrite because it's complicated for some reason. Simplify the right side. 4, differentiate implicitly. With respect to x. 5, solve for y prime. And replace y with f of x. So the process above is log differentiation. It is convenient. Necessary. Necessary is a very strong word. I'm going to show you a slight alternative to this. It is convenient to use it in the following situations. So that was the process. When would you want to actually use this? Because technically speaking, this can literally always work. It might not be useful though. So when would we use something like this? Well, for one, if the power in an expression we want to differentiate is complicated and variable. Right, so it's not a constant power. 2, if the power and base of an expression we wish to differentiate has variables in it. And 3, if we have a complicated expression where we would use the product and/or quotient rule to evaluate, but using them would be hella annoying. It's not an official term. So let's actually do some examples. Differentiate the cube root of x to the 7 e to the 3x over x plus 1 to the 4th. That's something that's sort of complicated. It's not the most complicated thing. I could give you much more complicated things to worry about. But let's say you wanted to differentiate that, the cube root of that thing. Now, hopefully you can appreciate that would be hella annoying if we did it directly. All right? Hopefully you can appreciate that. You would need the chain rule because you have that 1/3 power on the outside that you'd have to differentiate the outside function, multiply by the inner function. The inner function, how do you differentiate that? Well, it's a division of functions, so you might think, okay, I would use the quotient rule. However, when using the quotient rule, what would happen? Well, I would have to use the product rule to differentiate the numerator every time I'm differentiating the numerator. I would also need the chain rule to differentiate the e to the 3x and the x plus 1 to the 4th, right? So there's a lot going on here. Like I'd have to use the chain rule with the quotient rule, with the product rule, with a chain rule again. It's not going to be a fun time, okay? However, and this is something that I suppose some of you in the test didn't realize, when we have a logarithm in front of a complicated expression, it's actually a benefit. I had quite a few people in the test. There were a couple of times I actually differentiate something with an ln in front of it, and everyone ran directly into, okay, u prime over u, let's do this. I'm like, you wanna? Yeah, I was like, there's like a log there. You could have like broken it up into little small pieces. Yeah, so a lot of stuff happened there, where people decided to like run straight in, and it's like, yeah, they couldn't simplify in the end to get to what the final answer looked like. Whereas had you just used the log, break everything apart into little pieces, you would have differentiated very easily and figured out which one of the answer choices it was very easily as well. So yeah, so it turns out, because we know whenever a log is in front, it's super convenient and we don't just rush into things and not forget, we would in this situation be like, man, I wish there was a log in front of that thing. That way I could break it up into little pieces, because that's what I would do if there was a log in front of that thing. However, there isn't a log in front of that thing, and you can't just randomly put a log in front of that thing. So what you can do, though, is you can set up an equation that allows you to put a log in front of that thing and then use log differentiation. So here what we can do is we could set y equals the cube root of x to the 7th e to the 3x over x plus 1 to the 4th. We could log both sides. And then we can use the laws of logarithms to simplify the right side. Now, that would give you 7 ln x plus 3x minus 4 ln x plus 1. And then we differentiate. So I get y prime over y equals 7 over x plus 3 minus 4 over x plus 1. And so this means that my y prime is equal to 1/3 times the cube root of that whole thing times this guy. Well, it's x to the 7 e to the 3x over x plus 1 to the 4th. Okay. Now, I mean, you can try this without log differentiation, because you can do it. Like, we know all the rules to actually do this without this. Try this without log differentiation. Tell me how you feel about it. I always encourage you guys to try. you don't always have to take everything I say on faith. Sometimes you can be like, yeah, maybe Jhevon is he's just saying this. And just because, I don't know, he likes to talk or whatever. So sometimes when I go through and I recommend certain things, you can just be like, you know what, I'm gonna try not doing that thing. You might like it more, you never know. So I definitely encourage you to actually try. I think you'll like this way better though, just a hunch. And for those of you who on the test did not use logarithms to your advantage, I would encourage you to go over your test and then start using them to your advantage and see how different the test would feel. I don't get the sense that a lot of people ran out of time. Most people did pretty much everything. The only thing that people didn't do everything is in the bonus problems, which is technically fine because it was bonus, it was extra. But you would have had way more time to look over your work and tackle some of the bonus problems had you done things a lot more efficiently. So yeah, that's log differentiation. That's the process. Set up an equation, log both sides, use logs to your advantage to simplify the right side, differentiate, which in general, you're going to have easier things to differentiate. You're going to have nicer rules that you can apply. And then you multiply both sides by y. Here is another one. Differentiate this. Okay, someone quickly tell me what they would do here.
You set it equal to y.
Sure. Then?
You log both sides.
Okay, what would that look like?
Ln of y is equal to x squared ln.
X squared?
Yeah, it'd just be x squared.
Okay, and then?
Plus x squared ln x.
Okay.
Is it x to the 2 ln x then? Because when you first put it.
X to the 2 ln x?
Yeah.
No. But yeah, so far this is incorrect. But it's incorrect for probably a reason you didn't notice. Can you see why it's incorrect?
I mean, it doesn't look right, but I don't really get why.
Yeah, so I want you to get why. Does anyone see why this was incorrect? Like, how did you get this? What did you actually do?
Are you doing ln e to the x squared plus?
So you're doing ln e to the x squared plus ln of x to the x squared, right?
Yeah.
Is that allowed?
No.
Why not?
Because they have that x squared.
No, it's something simpler. I don't know, simpler. Because it's one of the things where it's not paying attention to what's allowed based on a rule. So So note, if we have y equals e to the x squared plus x to the x squared, and we log both sides, we get, okay, so go slower, don't try to simplify anything. What would it look like to log both sides? If I take the log of the left side, it looks like ln y, right? What does the log of the right side look like? Well, the right side is this whole thing, right? Correct? That's the entire right side. So if I take the log of the right side, what is inside the log? Well, the entire right side, right? This is the log of the right side. Now, this is correct, what I just wrote here. This is actually true. That line is correct. So here, the mistake happened when we have the ln y, and you think that this is how you should proceed. Now, why is this a mistake is what I'm asking. What rule did you use just now? So the line at the top of the screen is correct. The mistake happened in the very next line. What is the mistake? Like what did we assume we could do that we actually can't?
Distribute across sums.
Distribute a log across a sum. Is there a rule that says we can distribute a log across a sum? Right? It is not true that log of something plus something is log of the first thing plus log of the second thing, right? So that's undo. So that's a mistake, right? So what you want to do, recall, it's ln of a product is what you get a sum of logs from, right? Now, again, admittedly, it's hard to actually notice that here, but the moral of the story is, yeah, the rules are important. Literally every step you make, there has to be a rule that says it's okay. Don't just assume you can log each individual term on one side of an equation. What rule would allow you to do that, right? When I say log both sides and you're like, oh, I just do the ln of the first part, the ln of the e to the x squared is x squared. The ln of that part is just going to be, I'm going to bring that. Well, no, you weren't even allowed to do that in the first place, because logging both sides means you're taking the log of a sum. The right side is a sum. And so you're not actually allowed to log each individual parts, because logs do not distribute across sums. Sure, if we were differentiating, you could think of it that way. Oh, I just differentiate one and the other. If I were taking a limit, I could do that. Oh, just take the limit of the first and limit of the second, right? There are tons of things in which I could do that. Not with logs though. Logs are different. And that's very important. But when you're dealing with a log, and you're obviously, when we're applying step 2 here, you really want to be careful. You have to know the log rules. Okay. But yeah, that's also a very common mistake. So I'm not picking on you or anything. It was a very good first attempt, but that's one of the ways in which not carefully thinking about what you're doing can really come back to bite you. This is one of those things where that makes people feel like, oh my, math is like magic here. I don't even know what's going on. Really, it's like, yeah, you're just not paying the deep level of attention to detail that you should be paying. Sometimes you just do something because you feel like it, but feeling like it should work doesn't mean it should work. You have to know that it will work. What you are doing would work in other contexts. It would work, like I said, if we were taking limits or derivatives. But at the moment, we're not doing that. At the moment, we're logging both sides. And so it doesn't work anymore. And we just need to know, once I'm going to pick up a tool and use a tool to solve some problem, I need to know how that tool works, right? You don't just, like, if you're a chemist, you don't just go into a lab and start mixing chemicals and just like, oh, this, I feel like, you know, this is a red chemical and this is a blue chemical, and what I want to get to is a purple chemical. Let's just mix them. Like, you know, like, what is the blue? What is the red chemical? What is the blue chemical? Like, what are they specifically? Are they going to explode when you miss them? You don't know, right? Like, so there are a lot of things in life where it's like, you just don't just run in and do stuff. You have to know what you're using and what the rules are for using that thing. So here we cannot actually do log differentiation in this way. So to do log differentiation using the process I showed you, I'm going to show you how to do that. And that's actually going to help me segue into the next thing that I wanted to introduce, which is just an alternative on the log differentiation rule. So here's how to proceed with the process we developed. Now, logs do not distribute across sums. However, derivatives do, right? So recall, derivatives distribute across sums. i.e., if I wanted the derivative of e to the x squared plus x to the x squared, that's just the derivative of e to the x squared plus the derivative of x to the x squared. Now, the first derivative, we actually know how to do that without anything fancy at all. We have the derivative of e to the u is u prime e to the u. So that's not even a problem. I didn't even need log differentiation for that part. The second part, though, is the issue. And so what you get from this, so the idea is to separate them. I cannot log a sum. So what I'm going to do is I'm going to separate the terms and deal with them one at a time. Use log differentiation when I need to and don't use it when I don't, right? So if y equals e to the x squared plus x to the x squared, I can do something like set this to be, I don't know, f, and then set this to be g x to the x squared. And then what I notice is that I just need to differentiate each individual terms and then add the answers together at the end. Now over here, it's pretty straightforward. Your f prime is going to be 2xe to the x squared, okay? Now over here, when you're on the right side and you're looking at this guy, it's not something that you have a rule for. So here's where you're like, that's complicated. I don't have a rule. The power is an issue. There's an x squared in the power. It's variable. Log differentiation probably can work. So here you would log both sides. Log g is equal to x squared log x. And so then you can differentiate that. G prime over g is going to be 2x ln x plus x squared times 1 over x. So this means that your g prime is going to be g times g plus x. or in other words, that's going to be x to the x squared times 2x ln x plus x. And could simplify this. You can factor out an x out of here. Now, we know that y prime is just going to be f prime plus g prime. Because derivatives distribute across sums, I can do them individually. So that's going to be the 2xe to the x squared plus the x squared plus 1 times 2 ln x plus 1, where only one part I use log differentiation. Right? I can't use log differentiation on the total thing because logs don't distribute across sums. So what I have to do is I have to separate them, use log differentiation on the parts that need it, and then just combine the answers at the end. Which, that does seem kind of annoying. It's not difficult necessarily, but the fact that you'd have to notice that you'd have to do this, and just the fact of actually doing it, oh man, I have this one problem, now I'm gonna have to break it into two separate problems. Or maybe it was a sum of 3 terms, in which case you have to break it into 3 separate problems, right? And you deal with them individually and then add them together at the end. Psychologically, it's kind of annoying. So what I want to look at here, having to split things up, terms up can be annoying. So here's an alternative to log differentiation. Okay, now this one also uses a rule that we are very familiar with. We'll use the rule that if we have something as positive, then that thing is equal to e to the ln of that thing. Right? We had that rule. It was log rule 8 or something like that. So it's way back, taking it way back to like lecture 2 or something. And it was the rule that says a to the log to the base a of x is x, right? So if you have a base and inside that base you have in the power a log to the same base of something, then you can simplify that by just saying it's the thing, right? It's like the e and the ln cancel each other. We've seen this before, okay? So yeah, we can actually use that to rewrite something on the spot and introduce an ln without going and having to separately set y equals this, set this part equals that, set that, right? This will allow us to rewrite expressions on the spot and introduce an ln at the same time. Then we can differentiate via the derivative of e to the u is u prime e to the u rule. Okay, so let's look at this guy again. Okay. So we have to be careful with log differentiation because we realize that, all right, I can set y equals to this whole thing, but when I get to the log both sides part, that's an issue because I can't distribute the log across the sum. It's not going to allow me to actually simplify the right side. So you can do things separately, but that's kind of annoying. Is there a way to actually do it all in one? And the answer is yes. And I don't even have to go about setting y equals to anything. I can literally just go equals and move on to the next stage. This is going to be the same as the derivative of e to the x squared plus, now in the second part, what I'm going to do is I'm going to rewrite it as e to the ln of x to the x squared. Because e to the ln of something is just the same, right? The e and the ln would cancel each other. So here I rewrite. Can do it right on the spot. I don't need to go separately. Oh, set y equals this, set g equals that, because this is that, right? It's equal, right? It's just another way of writing the same thing. Like some people can write 0.5, someone else writes 1/2, someone else writes 4/8. You're all writing down the same thing. It's just that for whatever reason, one form might be more convenient than the other. So yeah, we would do that. Now, now we can apply the d dx e to the u equals u prime e to the u to both terms. So this will become u prime e to the u is 2x e to the x squared. Maybe I should take one more step and simplify so you can see how it would apply to the second one. Of course, this is going to be equal to the derivative of e to the x squared plus e to the x squared ln x. So now the derivative of the power, I would have to use the product rule. So differentiate the x squared, leave the ln, plus leave the x squared, differentiate the ln. And this guy was just me rewriting the x to the x squared in the first place. And again, I can factor out an x and then add it to the power here. So it's possible for you to do it all in one shot. So you got this derivative. Oh, I would just rewrite the second term as that. Fix the power by using the log rules to simplify it. Then just use u prime e to the u. And I have the derivative like that. So it's a very sneaky way, very slick way to actually apply log differentiation without actually going through the process of applying log differentiation, right? You just kind of rewrite it on the spot. And it's just convenient because you don't have to start with one problem and separate it into a bunch of separate problems. You can actually just do everything right there on the spot. So personally, I like this. You don't have to like it though. You could, want to do this, and that's completely fine. But personally, I prefer log differentiating in this way. But you can do either process you like. At the end of the day, using the log is going to be better than not. So as long as you recognize, hey, I want to introduce a logarithm here, then whatever way you want to do it, it's up to you. I'm fine with it. But you need to at least recognize in the first place that, yeah, I need a log in here somewhere, because that power, how am I going to deal with the x squared power? But you can do whichever variation you like. Yeah.
Would you be able to just scroll up one line? I missed the end of something. I just wanted to write it down. Right there. Yeah, thank you.
And just for comparison, let me just do the first problem again, just like this, just like do it all at once in one shot, the x to the x example, but I'm going to do the x to the x example with this version of log differentiation. Just for you to see it and compare, see how you feel about it. Find the derivative of x to the x, the question that started it all. Well, I would be like, well, this is e to the ln of x to the x, which is e to the x ln x. Normally, it's going to be okay to jump here. Just want to be a little bit thorough. And then I do u prime e to the u. Differentiate the x, leave the ln, plus leave the x, differentiate the ln. And so this is ln x plus 1, and this is x to the x. Right? There's the answer. And I can just do it all on one spot, as opposed to what we did in the beginning. Where is it? Yeah, set y equals this, log both sides, simplify the right side, take derivatives, rewrite, you know, and then come back and say, oh, the derivative of x to the x is this, which is completely fine. There's nothing wrong with that. But my personal preference would be to just rewrite it on the spot, use my exponential rule, and get to the answer that way. I encourage you to try both ways. Pick which way you like more. That's what you can do. I'll make, you know, from time to time, I'll make recommendations for sure. But at the end of the day, you are you. You might not like doing things my way. I would make recommendations that either go along with a personal preference of mine or just go along with statistics. I just notice usually when students do it this way, they get it right. And if they do it some other way, they get it wrong. So I'll recommend it to you. But even those recommendations don't really, you can take it with a grain of salt. You should really try. This is what, when you're practicing your homework and you're studying, these are the things you want to find out about yourself. When you're studying, you're not just studying the material, you're studying yourself. You're studying a lot of things. Like there are 3 minutes. I can't get into this right now, but that's a part of the idea. It's a very important idea. So yeah, let's actually move on. I want to do now that we have differentiation, implicit differentiation. Yeah, let's just talk about derivatives. Derivative rules and log differentiation. We can move on to a cool application. It's another special limit technique. Going way back to limits, remember I told you there was one step in the limit process when it comes to evaluating a limit about using a special technique. We had a bunch of these special techniques, and some of you use them on the exam, which I expected you to, you should have, about, you know, when things were top heavy or bottom heavy or blah, 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 you have a ratio of polynomials that you check the highest powers and you ignore everyone else. Highest powers are the same, it's the ratio of coefficients. If the highest power is on the bottom, it goes to 0. If the highest power is on top, it goes to plus or minus infinity, you just watch the sign. So there were a lot of these special techniques that I gave you. well, not a lot. In this class, I can't give you a lot because a lot of the limit special techniques have to do with trig functions, and we don't do those here. But I gave you a few special techniques, right, where you can actually do a limit without actually having to go through the major computation, right? So now I'm going to actually introduce a different limit technique to you, and it is called L'Hôpital. You have to say it with a French accent because it is named after a French person. So this is a limit technique, and it's named after a guy whose name means hospital in French. There were a couple years ago where I taught my class this, and the students just coined the phrase about taking things to the hospital. Or say, so how are we going to find this limit? Take it to the hospital. Okay, never mind. All right. So we use this to differentiate, not differentiate, find limits of certain, what we call indeterminate forms. So probably I should first introduce you what an indeterminate form is. Then I can tell you what L'Hopital's rule is about. So here's an indeterminate form. So these are limit forms. So it's forms that arise when you're taking limits. That cannot be evaluated at face value because of conflicting ideologies, processes, whatever. You'll see what I'm talking about when I do this. These are so there are about 7 main ones, and let's actually go through them. What do I mean by you can't evaluate it at face value? So here's one of them. Infinity raised to the 0. So you're taking a limit, the base is going off to infinity, the power is going off to 0. Now, what is that at face value? Well, if the base is infinite, it should be infinity, right? But whoa. The power is 0 though, so the answer should be 1. Is it 0 or 1? Civil war, right? So you now, like, we have everyone arguing about it. Like, you know, we have a bar fight in the math classroom because we have these conflicting ideas. Like 0 in the power means 1, but no, an infinite base means infinity. Which one is it? You can't really evaluate it at face value, right? Another one, 1 to the infinity. Well, it has base 1. The answer should be 1. Yeah, but you're raising to like the infinite power though. Like, come on, what to the infinite power? Don't you know about exponential functions? They go like this, right? Infinity minus infinity is 1. Isn't that 0? Well, not necessarily. Infinities can have different sizes, and infinities can be achieved at different rates. For example, if the first infinity is coming from me looking at e to the x, as x goes to infinity, and the second infinity is me looking at x squared as x goes to infinity, then the first infinity is not the same as the second infinity, right? The second infinity is, in terms of rates, going to be effectively 0 compared to the first one. So the answer in that case would be infinity, right? So one infinities Not all infinities are created equal. Not all infinities are achieved equally. Infinity minus infinity is not something you can evaluate at face value. It's not always 0. We'll see examples of this. Things involving infinity can get weird. 0 times infinity is another one. We're multiplying by 0. The answer should be 0, right? But yeah, we're also multiplying by infinity. So I feel like the answer should be infinite. Competing ideas. Which one wins out? I don't know. Depends on how you're getting the 0 and how you're getting the infinity, right? 5. Here's one that doesn't involve infinity. 0 to the 0. Okay, so raising something to the 0 power should give you 1, but if the base is 0, shouldn't it be 0? And in fact, I kind of explained why raising 0 to the 0 doesn't really make sense mathematically, because it would violate some other laws of exponents, but we talked about that a lot long ago. Here's a 6th one. Infinity divided by infinity. And of course, this one can be plus or minus. Right? Well, that's weird. Is it always 1? No, it's not. Again, one infinity can be bigger than another or achieved faster than another. You don't really know what that's going to be. It might be 1. It also might be infinity. It might be 0. The bottom infinity is bigger. It might be 5, right? Could be anything. 7. 0 over 0. Now we're getting really, yeah. I know if I put a 0 in a denominator, Jhevon's going to kill me. So yeah, this already has a lot of, emotional baggage attached to it. Yeah, division by 0, not really, not a thing, right? So, but that's very indeterminate. If your limit is going to a number over 0, then it would be easy in some cases to determine that the limit does not exist, or the limit does exist, right? You look at the one-sided limits. So you can see, okay, if I'm coming from this side, it's positive infinity. If I'm coming from that side, it's negative infinity, right? Think of like 1 over x squared as x approaches 0. Because it's a positive 1 over 0, something getting close to 0 from both sides, you can say, oh, it's positive infinity. Whereas 1 over x, you can make the determination that both sides give you a different thing. What is 0 over 0, though? Because now, whether this is plus or minus, you're not going to notice, right? You won't be able to play that same game, right? So this is also indeterminate. Can't evaluate it at face value. Now, not all indeterminate forms are created equal. In fact, these two are special. These two we can use L'Hopital's rule for. And only these two. So now you guys are probably going to start getting the memes that I put on a couple quizzes ago. Whereas like students always think they can hit L'Hopital's rule on anything, because the rule is very cool and you want to feel like you can always do it, but you can't always do it. You can only use L'Hopital's rule in these two very specific situations. If you're looking at a limit form that's going to infinity over infinity or 0 over 0. Often we can rewrite these, and you'll see how we'll do this in the next class, to look like one of these and apply L'Hopital's if necessary. Sometimes rewriting makes L'Hopital's unnecessary. So 1, you need to be able to recognize when you're seeing an indeterminate form. 2, you need to recognize what kind of indeterminate form. 2 of them are we can deal with very easily. The other 5, not so much. We have to kind of rewrite and finagle things a little bit with algebra before we do it. Now, let's get to the rule. L'hôpital. You have to say it with a French accent or it's not going to work. Well, it can, but it might give you trouble. You know, like how when you don't make the sound with your mouth, that you can't draw like a straight dashed line? Same thing. Or like you can't put on mascara with your mouth closed or something like that, I heard. So suppose we have a limit x approaches a of f of x divided by g of x. So this is a limit of a division. And f over g approaches 0 over 0 as x approaches a, or f over g approaches infinity over infinity as x approaches a. And of course, this can be plus or minus, plus or minus. Then the limit that we care about, the original, is equal to the limit of the following. Differentiate the top and differentiate the bottom. Whenever the original limit exists. This is called L'Hôpital's rule. It's the idea that if you're taking the limit of a division and the top and bottom are both going to 0, or the top and bottom are both going to some infinity, you can actually find that limit by differentiating the top, differentiating the bottom. And if you get an answer from doing that, that's the answer. It also I would want to note, we may apply L'Hôpital's rule. I'm going to abbreviate this L apostrophe H. You're going to see where I'm going to use this in a bit. Repeatedly in general. Just simplify between each application to make sure you have to do it again. You can actually apply this repeatedly. So you can differentiate top and bottom, you get another limit. Maybe that's another indeterminate form. Do it again, do it again, do it again. You can keep doing it until it's not indeterminate anymore. Simplify after each time you do it so you know you don't have to do it again. Sometimes you have to, sometimes you don't. But it's up to you to make sure. So I'm going to give you some examples. We're not going to do all of them. I'll probably run through the first 2 very, very quickly because I know we're already a few minutes over time. So examples to try. One, the limit as x approaches infinity of e to the x over x. E. By the way, you should know what that limit is off the top of your head without L'Hôpital's rule. But I decided to just start off. A and B are like that. But I decided to just start off with some limits where you know what the answer would be. And so it's not too jarring that the answer is going to, L'Hôpital's rule will actually give you the right answer. E is also something that you should know, but it's not as straightforward. It's a little factoid I gave you guys a while ago, and I didn't really emphasize it. But if you're rereading your notes recently, when I was introducing the number E, you'll actually come across what that answer is. So here are some examples. Let me show you how you would actually do this with L'Hopital's rule, and then you can try the rest for next class. So A. Okay. So first, quickly, what is the answer here? Tell me quickly. Well, anyone there? I want to rush through these, so don't be shy. Just tell me right away. We have a special technique, a lower level special technique that can deal with this, which, like I've been mentioning other times, use lower level techniques before you use more sophisticated ones. I don't want to keep you. It's infinity. We know it's infinity because it's an exponential divided by a polynomial. Exponentials move faster. Numerator is going to overwhelm the denominator. It's top heavy. Right? That's the idea we use when I want to say the numerator is going to overwhelm the denominator. Okay, so how would I use L'Hopital's rule? One thing is to notice that this approaches infinity over infinity, because as x goes to infinity, e to the x goes to infinity. As x goes to infinity, x goes to infinity. And here, you know, can apply L'Hopital's rule. Now, in this particular example, I don't think you should have to apply L'Hopital's rule because you should be aware that it's top heavy, but let's just keep it going. So I would write equal limit as x approaches infinity. And what I would write on top of that equal sign is a L apostrophe H. To indicate that L'Hopital's is being used. So then I would have differentiate the top, differentiate the bottom, right? So how does that, the first line become the second line? Because I use L'Hopital's rule, right? It's not true that I can just randomly replace x with 1 everywhere, right? That's not true. But by applying L'Hopital's rule, this is true. And so now I get the limit as x approaches infinity of e to the x, which is infinity, which is also expected. B. Limit as x approaches infinity of ln x divided by x. So 1, notice that this goes to, again, infinity over infinity. So we can use L'Hopital's. You shouldn't, though. It's bottom heavy. So we know the answer is 0. You can know that by looking at it. You don't. Right. So on a test, if I were silly enough to give you an example this simple, you would just write 0 because bottom heavy, and you move on with your life. You don't have to do anything complicated. However, just as an illustration, I can apply L'Hopital's rule here to say Well, if I differentiate the top and differentiate the bottom, that limit should give me the same answer. Well, I'm dividing by 1, so I just get the top. As x goes to infinity of 1 over x, the answer is 0, as expected, right? So that's just me applying L'Hopital's rule. You can do the same thing for all of these guys. Notice that some of these are indeterminate of another form, like this one would be 0 to infinity, negative infinity, right? So L'Hopital's rule does not apply directly to this, but you could rewrite it maybe somehow to get it to work. But yeah, try the rest of these for next time. That was L'Hopital's rule. A very cool limit technique. Whenever you're going to 0 over 0 or infinity over infinity, just differentiate the top, differentiate the bottom. A lot of times you'll get a simpler limit to have to deal with, and then you can deal with it then. So yeah, so here are those guys again in case you want to take a screenshot, and we will stop right there. So yeah, thank you for your time and attention. We will stop there for now. That's it. I'll see you guys on Thursday. Enjoy the rest of your week, and I'll see you guys in the next one. Ciao.